Okay, so this one I'll try to keep it just the processing part, and some of the stuff we said in the last session I'll repeat it just because the concept for a lot of people is new, and uh, they have sometimes they have a hard time grasping it. So I thought it'll be good to just repeat some of the stuff and maybe give you some problems to do it. So that way it'll. Okay, I think um, we kind of talked about like how do we get from circuit to package. Well, first you have to get to the physical design part of it, which is drawing this layout, send it to the fabrication house. They'll put fabricate all this on a wafer, which is usually 8-inch, or if it's an older process, then it's 6-inch. And like newer processes, like the ones where all the Qualcomm processors, Intel are done, they're actually 12-inch processors, 12-inch wafers. So they take the layout, basically tile it and copy it, make as many chips as they can on each one of them. But this is all done at once, right? Like as I was saying, uh, actually the photolithographic, the exposure is done stepwise. They don't have a huge mass like this. They usually have what's called a reticle size. So they'll keep exposing by stepping a certain size of these chips. But once the processing starts, it's, obviously it has to be done at one shot. It's not like a PCB where you're putting one devices each from the shelf and soldering it. Okay. Okay. So from the circuit, like I said, you have to get to this physical mass, and those physical mass will result in the actual devices after they have been fabricated. Um, and we'll look at again the fabrication process uh, for going through the entire thing. So the base of the one which we keep talking about, what's a wafer, the basis of doing all the monolithic devices is this wafer. And it's a process which has been used for a long time. Obviously, they have been refining it, but you know, on the outside, it is almost the same. The CG method is what they use to fabricate this. So essentially what they do is they melt a bunch of polysilicon. Polysilicon is polycrystalline silicon. It's because you need a crystalline base. You can't have polysilicon because it's too fragile and you can't create devices with it. So you need a crystalline device. So what they do is they take actually polysilicon, which is kind of a powder form of silicon, and they they melt it in this melting pot, big melting pot. And the amount of doping they need to do and all that is done here. And they introduce a small seed crystal. It's like doing dahi, right? You need like that seed dahi to do it. So that's the seed crystal they needed. So they put that seed crystal in the molten pot, and they actually very slowly keep pulling it because the crystals just form around it. They keep pulling it, and obviously it's a very controlled, very refined and controlled process. And eventually you get a big rod of this ingot. So you can see there are different sizes. So I think this probably is the 8-inch, 6-inch, and then maybe 4 and 3 maybe. And I would say the length is probably about 3 foot. This may be about 4 foot. Okay. So you get this large solid bar, which they call it as ingot. And then they slice it. So typically these are sliced to 5 to 10 millimeters sometime. And after you fabricate it, they can grind it down to like 500 micrometer. If you, a lot of times you need thinning to, especially to isolate it and sometimes to package it. Like if you have a thick wafer and you dice it, it's too thick for the package house to be packaging it. So you have to grind it. But when the wafer is like 8-inch, they have to have a certain thickness because otherwise it just becomes brittle and it'll break, especially for the bigger ones like the 8-inch and the 12-inch one. So they take a diamond saw and slice it, and after slicing is what you get these big 8-inch or 6-inch or 12-inch circular ones, which we call it wafers. Um, Sometimes somebody asks me, why is there a slot here? So pretty much every time you'll see the wafers, they have a slot. Uh, I actually haven't looked into it, but my guess is that that's for alignment. So because every process step I showed you, they are not done in one place. Each process, like the doping is done in one place, the CV will be done in another place, the metallization is done in another place. Um, there's actually a great video which just recently came out. The Intel CEO, they're interviewing Intel CEO about the supply shortages. He's actually taking you inside Intel's Foundry. So if you search on the web, you'll see it's 60 minutes. Search for 60 minutes Intel CEO. Intel CEO, you'll get it. And you'll see when he's inside the Foundry house, you'll see this small little, you know, it's like that Monster Inc. Small little caddies, which is carrying all the wafers on the top. You'll see there is carriages. They're putting it into different places. So, the foundry is a huge place. And so these wafers get placed. So like, for example, they'll grow silicon dioxide first, and then all the wafers will come out and obviously sealed, vacuum sealed and all that. And they go to another place and so on. So I think having this tab keeps them aligned, and when they go to the next step, because when they take the mask, it has to perfectly align with the previous one. If it is not, then everything is a short, open. The whole thing is, and that's the challenge, and that's what I was telling about why the self-aligned gate is probably what's made Moore's law possible. Okay, photolithography. I think I did talk a little bit about it. And that's the kind of the main processing step in most of these steps. Some of them are just plain like diffusions or growing oxide, but any kind of patterning is required. It is photolithographic. And guys, give me just a second here. Okay, sorry about that. Um, so yeah, so most of these patternings are done through this photolithographic, where I showed you where you take the material you need to be patterned. For example, in this case, this is the substrate. So this is the big giant wafer. So you're just showing a small section of the cross section of the wafer. And then let's say you grow silicon dioxide over here, and you want to pattern this silicon dioxide. Then you first put photoresist, um, and then get the mask. And like I said, depending on the mask, if it is a positive mask, it will block the UV. And if it is a negative mask, then it will allow everywhere else. I mean, allow here and block it everywhere. So then what it does is the place where it is blocked, it is hardened by photoresist. And I mean, wherever the UV shines in, it is hardened the photoresist is hardened. Wherever it's not, it remains soft. So then what happens is after that you do a chemical etching process where it just etches this out. Okay, selective etching process. It etches this out, and you have rest of it which is there. So if you wanted to do a negative, sorry, this is a negative one where you wanted to etch out this thing. I mean, sorry, positive one where you want to etch out. If you don't want to etch out, you do the negative one. Okay, and that's just decided by the kind of layer you're trying to do. Okay, so I think I've gone through this, so I'll just quickly go through this again. So you have a wafer, and this is, by the way, wafer, not water. Looks like water there. Wafer, and let's say you have this material which you want to pattern. So it can be silicon dioxide, metal, or depending on the step where it needs to be patterned. So you first fill that, or either it's grown or ion bombarded or whatever way it is, and then you put photoresist on top of it. And usually they put the photoresist and they do a high spin. So when they do that, the resist actually kind of evenly spreads out with a certain micrometer length, and the material is underneath that. Then you take the mask and you shine UV light on top of it. And like I said, depending on the mask, either you allow it to pass through the mask or mask it. And depending on that, either it'll keep the mask area on or it'll off. In case, for example, here it allows the UV to go in and it makes it soluble photoresist, and that's what allows you to uh, take it out. Okay, and then you use a selective etching process, and the selective etching process is basically the ones where UV is exposed to a little bit. And again, the etching process also, you can have two. You can have etching process where it'll etch away the hardened stuff. You can have etching process where it'll take away the soft ones too. So it depends on the process and uh, how fine you want to do it and all that. Okay, and after that you again remove away the photoresist, which is again a selective etching. It's a selective dissolvent. So solvent meant only for photoresist. You just put that and spin it, and then all the photoresist is basically gone. Okay. All right. So now that I have repeated twice, let me see if you can do it. So this is a exercise for you guys. So I'll tell you what the exercise is, and then you can do it. And it's the same one for the today's assessment test too. So do it, then you don't have to do it then. Okay. All right. So this is what I've drawn as a mass, just one single square. And here I'm saying I want to pattern the metal. So um, so when the chip comes out, um, I want on the wafer, I want silicon dioxide on top of it. I want this metal layer. Okay. So what I want you guys to do is, I want you guys to go through each of this step. So for example, I want you to first grow oxide and then deposit metal, apply photoresist. You show these expose, and then you show to all the metal layers. So as you're going through these steps, show me how the cross section is going to look like. Okay. So for the assessment, you can keep this, and what you do is you just upload the JPEG or PDF. I actually, I'm not sure how you can upload it. I haven't used it either. This is actually, we are using Puneet's portal. So Santanu, do you know how they can upload it? It's probably there as an option, right? In there.
So till now, I don't know. So
Okay.
evening, Puneet sir will discuss with me. Then we'll.
Okay. Yeah. When you go to there, a lot of the multiple questions, you can just obviously answer it. These ones, there is, I know there is an option to upload. So either you can just take a picture and upload it, or do a PDF, upload it. But whatever you do, just make sure the size is small. It probably has the limitation. Okay. All right. So I'll wait for a few minutes for you guys to do this exercise. Yeah. Do you have any questions about what the question is about? What is the grow oxide part? Yeah. So, one of the reasons people use silicon dioxide as a insulator in silicon, the IC design is because you have silicon, it's very easy to grow oxide, and growing oxide is nothing but exposing your silicon wafer to moisture basically, and they just pass water vapor into it, and the silicon oxidizes, and that oxidation just keeps growing. Okay, and that's how you actually form silicon dioxide, and then they take it out, polish it, and then grow the next layer and so on. So when I say grow oxide, it's basically the first step for you to do is oxide. So okay, let me do this. What I'll do is, you guys carry on, and maybe I'll just give you some intermediate steps. Okay, so if I draw the cross section, so obviously you're going to get this wafer, right? So this is what you start with. Okay, and that's all you need to start with. And the first step, so I'll maybe do the first step. Once you do, let me see which color I want to choose, maybe blue. So after, I haven't obviously give you thickness and all that, but just these are arbitrary. So after the first step, step 1, this is how your chip is going to look like. There'll be so this will be your oxide, which is silicon dioxide. Okay, so this is step 1. Now I want to show, I want you to draw what will happen in step 2. Okay, and eventually what, so you're going to draw for step 2, 3 and 4, and then I'll draw the 5 maybe for you. So I'll draw actually 5 right underneath this. I'll draw 5 here. So in 5, so this is your silicon, this is your P minus substrate, let's say. This is your wafer basically, just showing a small portion of the wafer, right? So after your step 5, this is what you should get. Kind of roughly hard to draw a straight line. All this is your oxide, and then this is your metal. So this is your metal. Okay, so I did step 1 and 2 for you, so you need to do 2, 3 and 4. So everyone clear about the problem now? So basically how you got from this plain just this substrate to this by going through these 5 steps. If you still have any questions, just ask. Right? Oh, sorry, forgot to. Yes, Antanu, just whenever I forget, just start the recording. So I didn't want to have a blank. So let's say I wanted to have a hole here. Okay, instead of this metal, what I wanted was this. Silicon, I'm sorry. I wanted to have this. Right? So basically that's what I call it as a negative mask, right? Negative mask in the sense that wherever there is a mask, I want the pattern to be etched away, not there. Here I want it it to be here. And that's something decided within the foundry design rules. So basically, when they give you a device and they say these are the set of masks you need to do it, those are all preconceived. You don't tell the foundry that, oh, do a negative mask here. That's all the foundry guys have figured it out. So all they ask you to do is like, okay, wherever you want metal, you just draw this. Wherever you want diffusion, you draw this layer. Wherever you want poly get, you draw this layer. And the negative and positive and all that is basically done by that. So if you did this with a negative mask, then what would happen is here the UV was allowed here. Now you want the UV to be allowed everywhere else but the mask area, right? And if you do that, then these are the ones which becomes hardened and this becomes soluble, and you etch this away and then you remain here. Now, you could do this with a negative photoresist in the sense that here we are assuming that wherever the UV is exposed, then that is the part which is hardened, and that part of the metal or silicon dioxide remains. Everything else actually gets etched away. But you could use a type of photoresist which does the opposite. Okay. So this is really a processing thing. They decide which one to use. I'm not a processing expert, so I don't know where they decide on what, but I'm just telling you there are different ways you can do negative masking or negative photoresist. Okay. So basically uh, here we said wherever it is exposed, keep that. If you did a negative photoresist, then it will just remove this away. And even with this mask, you'd still get our original, this thing where you have the oxide and this is your metal here. Okay, did that make sense? Positive photoresist hardens, right? I think so. I forget what the convention is, but yeah, photoresist, I think positive, they mean that wherever there is UV light, then it hardens and that you cannot etch it away. So I might be, yeah, I forget what the thing is using, but yeah, I
So,
think it is correct.
sir, screen is not visible. Is it?
Oh, is it, how about now? Can you see now?
Yes, 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 sir.
Okay. Okay, yeah, I think Krishna Madhu says yes, so he must know processing very well. Okay, thanks. Okay, so clear? Seriously, did that make sense? Okay, good. I mean, sorry, Bijay Lakshmi. Yes. Okay, so now I'm going to show you some few very simple ones, so that way you get an idea on how things are done. And it's good to, even if you are just a verification designer, it's good to get an idea of these, because once you start talking about devices, you get a better feel of why certain rules are, especially when you're writing design rules, DRCs and all that. um, it kind of gives you that extra depth of knowing, like, okay, this is why we need a rule here, this is why the processing steps for locus didn't work in one place compared to the other, and so on. Okay, so it is kind of good to know that. So so this is, I'm just showing quickly, I'll just show you how diffusion and ion implantation is done. And like as I said, depending on the tech, and the, these are all economic decisions, they're cost decisions, right? So sometimes you'll ask, oh, why are they not doing STI for this process? Why are they doing locus? Well, um, they're selling the chips for like 1 rupee. Okay, they do the STI, they're out of the business, right? Because that's an expensive process. So if they don't need it, they don't use it. So it really depends on the type of process and the application people are doing. So a lot of these are actually cost decisions, not just technology decisions. So a lot of times people think, oh, why are they not doing this? This is so better. But yeah, it's most of the time when they're better, they're also expensive. And if they're expensive, most of the integrated circuit market out there, they're super price sensitive. Okay, and so anything they can save on, it is helpful. So this is like an old diffusion method of creating N-well, and I'll show you the ion implantation right after this. And people still prefer the um, diffusion method for cheaper technologies because it's just a cheaper process. But the problem with diffusion is for low feature length technologies, it is difficult to control the edges, right? So for example, here you've seen, so when have been showing you the PMOS example, I mean the inverter example, you for the PMOS you need to create an N-well, and we'll go into this when we start doing the devices. That's because you need a P plus, you need a P plus as source drain, and you put the gate and so on. So you need what's called an N-well because this substrate is P type, right? It's a P type material. So obviously if you do a P plus, then it'll just short, source and drain will just short with everything, every other source and drains. So first you have to create an N-type well, right, inside this P substrate. If you're creating an NMOS, and if it is not what's called a twin top process, like the old locust process, then you just do N plus here, N plus here, and put your thin oxide gate and so on. You start doing the devices. But for the PMOSes, you need to do the N-well. So this is how you do the N-well. Like, um, so what you do is you first deposit silicon dioxide like it's shown, and then you etch away. So let's say I have drawn in the mask, I've drawn an N-well area. That's the area which is going to get etched away here, right? So you'll have a mask over here, which you would have had photoresist, and you expose that, you do photoresist and all that, and then you etch away. And then now you have this exposed P substrate to the outside wall. And then what they do is they take this gas containing phosphorus, because that's what they want to create the N-well with for the N type. And then what they do is that at a very high temperature, they just run this gas and it just diffuses in, right? That's why it's called a diffusion process. So it gets diffused in, and that's how you create an N-well process. But the problem is, because it's a diffusion process, it also diffuses to the side, right? So it's not shown here, but it kind of does that, right? So when you draw an N-well like this, when it comes back, you actually get an N-well which is bigger, right? So it is less but like I said, for older technologies which are large feature length and all that, they don't care, as long as within the design rules, as long as they put it the PMOS. But if you're making too many devices close by and you want to control that diffusion length, then because this is process dependent, it's not optics. So if you diffuse it, if it grows by 1 nanometer or 2 nanometer or 40 nanometer, and you're trying to do a 2 nanometer design, then you're host, right? Because every N-well is a short now. So so this is good for cheaper, and it's an older process, cheaper process, and it's a pretty simple process. You just expose it to phosphorus gas, and for how long ever you want it, and you get N-well basically out of it, right? The next one is ion implantation. So in ion implantation, what happens is you basically, if I just redraw this, you do the etching and all that here, but instead of passing this gas, you actually bombard it with phosphorus ions. Okay, high speed, really high speed bombardment you do. I think I have, yeah. So when you do, let me just erase this. So this photograph I've shown here, this wafer is here. So you can see there's a small mass here. That's this opening here, basically by the silicon dioxide. So you have an ion source, whatever ion you're trying to create, phosphorus or whatever ion you're trying to create. And there's some electromagnetic focusing lens. It goes through this like sort of a waveguide for ions, and it just bombards it straight into the thing. But the thing is that when it bombards it, it just goes straight into and gets deposited like at a certain level, at a certain height. And then what they do is they heat it, which is called annealing, I think. Yeah. So what you do is once you bombard it, so I've shown here, so let me see if you can make sense of this. Um, so once this is bombarded, like as I said, it's going to be mostly concentrated in this area, which I've shown with this profile. You can see this profile. So most of the ion concentration is, sitting somewhere right here, but you want this whole area to be n-type. So what they do is they heat it, and once they heat it, it basically anneals. It like basically just kind of diffuses all over, and this dotted line what you see is after annealing, and that uh, allows you to seep through it. Now that also diffuses to the back, but it is much better controlled than straight diffusion. Okay, so for example, here I've shown 1000 degrees centigrade for 10 to 15 minutes, and that does it. And some of the other processes are much tighter, so they'll do ion bombardment and shorter annealing, because they have just improved the processes basically. Okay, so makes sense, how n wells are created in both the process. Or any questions here? Okay. Okay, so transistor isolation. Um, so now this is a monolithic wafer, right? So you have one wafer, and it's not insulating. The p-type substrate is actually conducting. Now it can be highly conductive. The conduction can be small, but it is still um, conductive. So you have to design it in such a way, the processes. So you want to make sure that all these transistors, which are kind of made in isolation and separated by certain distances, they don't start talking to each other or shorting each other, right? So that's the whole idea of transistor isolation. So here, for example, I'll show you, this is the N well, and let me draw. So you're going to have basically, let's say P plus here, P plus here, and then you'll have an N device, which is some N plus here, or over here. Maybe, I don't know if I've shown you in that. Yeah, so these are the devices, and these are the ones where you want to block it. So here's the thing. So let me show it to you here. So this is, let's say, let me draw it a little. So let's say this is your substrate, right? And you did a PMOS where you did P plus gate and all that, and you put N well here, and you did N plus, and obviously a lot of you haven't done the device part yet, but essentially what you're trying to do is you want to create a channel between these two, source and drain, using a voltage control on this gate, right? And then this whole thing is buried in silicon dioxide, and you have metal routing, right? So let's say there is metal going on here, long piece of metal going on here. You apply a voltage. Now this silicon dioxide might turn on a channel here and short it, because this also looks like a MOS between this device and this device here. If there is a channel here, they'll conduct, right? So that's the whole idea of isolation, is you want to make sure that you don't accidentally short two devices which are adjacent to each other by having some other metal layer actually form a channel. Okay. Plus, you don't want to start cross-talking because of the substrate itself, because this substrate just looks like a resistor which is connected from here to here as well. Okay. So the way it is isolated in locus processes, what they do is, and this will be more clear when tomorrow we start talking about calculating the VT, the threshold voltage for MOS devices. This will be a little bit more clear, but you just kind of take it for granted here. So what they do is, in the places where you want to have device, you want to be able to turn on the channel when you put the gate voltage to a certain voltage, right? So let's say, for example, the process you're going to use, it's a 5-volt process or a 4-volt process, and you apply a gate volt of 1 volt, the channel will turn on and it will conduct. That's because that's how the process has designed those devices, by doing all this process engineering. Now what you want to do in between the devices is the opposite. You want to implant these things in such a way that even if I put 100 volts, this channel doesn't turn on, because this also looks like a channel. Like, because, like for example, when I draw this substrate, I have a P plus, I have a P plus, I have a P plus. I put a gate here, but if there is another oxide here, another metal here, this is also a transistor. It's a weak transistor, but it's still a transistor, although you didn't intend to do that, right? Your next transistor was here, let's say. So, so they do these implants in the P substrate such that even if you put a really high voltage here, this will take a lot larger voltage to kind of create a channel here to short the two devices. And like I said, it'll be more clear when we start talking about the threshold voltages tomorrow. So that's what they do for transistor isolation. So essentially for transistor isolations, wherever the transistors are not there, they will take those areas and implant with a sort of an opposite ion so that it is very difficult to turn it on. That's the whole idea. And this is a good place for using negative mask. Negative mask. So this is where do they do the boron implant? Wherever there is no diffusion. Okay. So for example, in order to do a transistor, you usually do a diffusion and you draw a gate length here, right? So, you know, these implants, they do it wherever there is no diffusion. So they'll do a negative mask of diffusion. So they do a positive mask when they want to create the source and drain and do P plus implants. For these boron implants, they will take the negative mask of this. So they will basically do the implantation other than the place where there is the active or the source and drain area. Okay. All right. So is it sort of clear so far? Any questions? Okay. And the locus usually starts for local oxidation process. This is like one of the oldest process. So the one example I showed you, which I'll show you again, that's called STI, shallow trench isolation. And okay, and this is just showing you the follow-up steps. So what they do is you do this implant and then you grow what's called field oxide. So the larger the oxide depth, the harder again it is to turn it on, right? The smaller it is because your electric field is higher. If I put a voltage, so voltage, you know, your electric field is voltage over the distance. So if you're increasing this distance, then this electric field is lower. If this electric field is lower, then the chances of turning this on is also lower. Okay. So they do the implant and then they grow the oxide, which is called field oxide on this. And this is part of the locus process. Now, like I said, this is an older process, but in newer processes, for finer technologies, they don't do this. That's because you just can't have really fine transistors with this, because as you can see, these take away a lot of areas while growing these field oxides, because they have a kind of a slope to it, right? It's not like abrupt like this. So they have a slope to it. So in order to isolate it, you need a minimum distance between the field oxides. So when you get to like, you know, 180, 130 nanometer or 65, 45 nanometer gate lengths, these things, the locus will not work. And that's where the shallow trench isolation process is used. So here what you do is instead of doing all the implants and all that, they actually do a trench. Okay. So basically you're going to have your, yeah. So you're going to have your, you know, your P plus devices here and, you know, your N plus devices here, your NMOS is here. So in order to isolate them, then they actually dig a trench and fill it with silicon dioxide. Okay. And this process, what it does allows you to do is gets much finer um, finer pitch length. Okay, is there a question? So Ashwin, you have a question? Oh, what is the function of Si3NO4? That is just the way they do the shallow trench isolation. Okay. So that's a silicon nitride they use to do. Yeah, I don't know exactly why they use it for, but you can look up into it. But that's what they use for shallow trench isolation. But essentially, the idea of the shallow trench isolation is you're trying to avoid it, and you still, have this path, a resistive path, but now it's a longer resistive path to connect between two diodes. Okay. And this shallow trench, most of the processes, especially in analog, when you use 130 nanometer, 65 or 90, 180, any of these, they're all mostly shallow trench isolated process. And this does give you some extra problems associated with them. Mostly what they do is they put a lot of stress on the devices right next to it, and they change the parameters of those devices. And so when you design this, you want to make sure that your devices are substantially away from the shallow trench isolation. Otherwise, when it comes back, it may not meet your model parameters, the parameters which is. Okay, so the question is, Sumiranjan is asking, in STI, the P well and the N well will create a the STI in the P well and N well will create a capacitance in between them. Yes, but it's a really thick trench isolation, which is still much better than having a resistor, right? Because your DC resistance is basically infinite, whereas you have finite DC resistance here. So, but this shallow trench isolation, the capacitance is like attofarads. So it's pretty much negligible for most cases. So yeah, you don't have to worry about that capacitance. All right, any other questions regarding the transistor isolation, why you do it, how we do it? Okay, so the transistors, when they're created, you basically need a really thin oxide between the gate and the substrate, right? That's how you get these faster transistors, or high gain transistors to do amplifiers, high speed amplifiers, and so on. So you already saw like how we do thin oxide, and then you grow the thick oxide. You do the P plus implant to isolate these devices. Um, and then for NMOS, so that was for PMOS. Wherever you want to do NMOS, there is what's called gate threshold voltage adjustment implant. So here you do the opposite. Here you actually do the adjustment so that it allows you to get the threshold voltage you want, right? For example, if you're doing 0.18, you want a threshold voltage of 0.5 volts or 0.4 volts. You do that implantation, and we'll go into pretty detailed theory of how to get this, how to control this tomorrow when we do the threshold threshold calculations. Okay, so the polysilicon, I think you guys are pretty familiar with it right now. So you take the polysilicon mask, and you essentially, after the thin oxide is grown, you grow the polysilicon on top of it, etch away the non-gate part of it with the photoresist, and then you're going to get basically your substrate, your thin oxide, and then this is your gate, right? So and this is done all for all the devices, both for the NMOS and the PMOS devices, right? And after that, you um, do your and this the source and drain junction, like as I said before, you instead of actually doing so for example, your first intuition is like take the mask. So I drew, so let's take the layout. So I drew the diffusion, I drew the gate, right? So your first inclination, or in fact that's how first people did it, is that um, you take this area and you take this area. So you take all the diffusion area which is not overlapped by gate. So this is the gate area, and you create your P plus or N plus in those areas, right? The shaded areas. And then you create the thin oxide and poly separately. The problem with this is, like as I said, is this needs to be perfectly aligned. But it's very difficult to align in this. Like when you are having 4 nanometers. So right now, you have 2 to 4 nanometers of this thing. Most processes, when you align it, you can't even get a nanometer in them. And so what will happen is you do your P plus, first, and then when you do the gate, it'll be shifted like this. So this is open, right? Because you don't have a gate in this area. So what will happen is this will become an open device. So with self-align, what you do is you basically first do the gate and use the gate actually as the mask, right? And then you bombard the ions. So all over the place, except, in the mask area, the diffusion mask area, including the gate area. And then what it does, it just by the virtue of the polysilicon just masking it, it will just implant the ions in the source and drain area. Underneath the gate, it will be stopped by the polysilicon. Okay. And the gate, you ideally want it to be metal. Okay. You want it to be metal, and that's how it was done in the very first processes, like 1 to 2 micron processes, where they were doing it in this fashion. It was easier to do it then. They would do the source, they would do the drain, they would put a thin oxide, and they will put the metal after that. Okay. But in the self-aligned process, it's very difficult to do metal. In fact, you can't do it, and that's why they use polysilicon. But polysilicon is very highly resistive. But the thing is that when the ion bombarded, so let's say you are bombarding with this with some positive ions, that positive ions also get bombarded into the polysilicon. And what they do is they anneal it, right? I showed in the last slide that they bombard it and they anneal it so that it diffuses in this whole area. That also diffuses in the polysilicon area, and that makes it actually more conductive. But it so happens that it still is not conductive enough. So they do something called salicide. They will put a very thin titanium layer on top of the poly to make it conductive. But essentially, this self-align thing helps both to align your source and drain as well as make your poly gate conductive as well. Because there are a lot of processes where they don't do the salicide, and just bombarding them with the ion and annealing it, it's good enough for a lot of the applications. Okay. So is the self-align part pretty clear to everyone? Why we are doing self-align in the processes, or any questions? Okay, yes, sir, clear. It's mostly coming from one or two guys. Hopefully everyone else is at least getting an idea. Okay, good. Just give me a second, guys. Okay, that's a great question from Prachita. Says, in case of putting salicide for improving conduction in polysilicon, can we put a mask over it and then bombard ions? Yes, great. Yeah, you don't want to salicide on, so just maybe I can quickly show what salicide means here. Um, so what you did was you drew a layout, something like this, right? That's your diffusion, and this is your polysilicon, right? So let me start with the substrate here. So here, this whole place, you you first do a thin oxide here using this mask, right? Using the gate mask, you do thin oxide. Using that gate mask, you do poly, right? So you're still using this mask. And then you use this mask, this entire diffusion mask, which is this whole area. So that is this whole area. So that will bombard the whole thing and it will create the source and drain. So let's say this was a PMOS, so this will be P plus, this will be P plus, and this poly becomes a P type as well. Okay, so this poly is also a P type and becomes really conductive. And like I said, um, for some processes, for some application, this is not good enough. It's still, you want this gate to be as high, low conductive as possible. That means low resistance. I mean, high conductive and low resistance as possible. So it's not good enough. So most processes do what's called saliciding. And for saliciding, they will use the poly mask actually. So they will mask out everything else, right? So the mask will mask out everything else. And they'll actually put a layer of salicide and sort of etch it out or ion bombard it just basically and do the saliciding on this. So yeah, they use the basically the gate mask to do saliciding. And if it seeps into some of it in the source drain area, it's fine because it's just conductive. So they make sure that because you could have the width of the salicide could be less, but you don't want to be more, right? It's so they just take care of that in the process. And the resistors in IC design process, and again tomorrow we'll talk more about resistors. That's actually done through the same polysilicon as gate. Now what they do in resistors is basically because you want that to be highly resistor, so you actually don't do the saliciding. So they stop the saliciding to give you a high value of resistance. So that's how you fabricate resistors in most IC design processes. You actually use the same polysilicon you use for gate, but instead of using it on top of a diffusion, you just connect from one end to another end, and you get a resistor basically. Okay, I hope that answered your question, Prachita. Okay, this is just showing you, after all the polysilicons are done, you put photoresist, and how, just showing the same steps we have been talking about, just putting photoresist using the same set of masks we have given them, either as a combination of them or negation of them, doing the same mask. Basically they just keep repeating all these processes to do the devices, the isolations, the source and drains, the gates and the connections and everything. Okay. And then once all the metallization, everything is done, if you look at the cross section of, let's say, this P and N type device, uh, this is what it looks like. I mean, it's kind of exaggerated, but it does look very sort of unwieldy and all that, especially the old process. Now they do what's called CMP. It's a polishing steps, because if you have so much undulation, it's very hard to get very fine line features. So what they do is after every material, every step is grown more thicker than it is needs to be, and then they polish it. So by polishing it, they actually kind of bring that tolerance down a lot. And when you start doing a DRC for larger chips and all that, you'll see all these density rules. You have to have a certain amount of metal in every area of your chip. You cannot have like a millimeter square of area and just have one end metal 3. If you don't have it, you have to fill it with metal, just floating metal, because otherwise this whole polishing process will just fall apart. And that's true for all fine line technologies. The old ones, it's not as much necessary. Okay, so I'll show the steps again, the STI process steps again. Like as I showed before, this is, for example, is an example of just a NMOS, PMOS connected. Their sources are connected, drain connected to maybe VDD and so on. And you draw this layout. And for each of these masks, hopefully now it makes more sense, like how it steps. When I first showed you, I just said, just imagine this is converted to this step here. So here you can see how they use the mask to take that layout and basically convert it into the physical layer. So for example, in this layout, you can see this is the diffusion area. This is the well area. So you have your P well, N well, and this is the diffusion area, which defines your source and drain. This is your gate. This is your gate for the PMOS. And this is the metallization. This is the via, which connects between metal to the source and drain underneath it. And what you do is you just do layer by layer, right? So this is the diffusion layer. You take that, the N well and the P well layer. So you take the P well and use that mask to create the P well through diffusion or ion bombardment and alignment, and then use the same mask to do the STI process basically. Wherever you have these non-diffusion areas or non-well areas, uh, uh, so they use the mask. So basically, to create the STI, what they'll do is they'll combine the P well, N well, take the inverse of that, and create the STI. So basically, you want STI wherever there is no P well or N well. So all this should be STI, right? So this is all STI, shallow trench isolation. So they'll take the P well mask, they will take the N well mask, and what they'll do is they'll call ORing of the mask. So basically, wherever there is a P well, N well, those areas will be masked. Everywhere else, the STI will be done. Same process again. Take the mask, do photoresist, shine UV through the mask, etch it, do the STI mostly through oxidation. Trench it first, then do the oxidation, remove the photoresist, and then you'll have this, right? So the same drill. And again, using uh, the well areas, they'll first do a thin oxide all over the place, and using the same photolithographic process. Then they take the gate and then etch it away, right? So you don't want this thin oxide everywhere. So they'll take the gate mask and basically etch all these away after they put the polysilicon on. So they'll first deposit the polysilicon and then they'll etch it away. And then now you have the gate, the thin oxide, and you have your wells, right? So this is your P well, this is your N well. Okay. Now tell me, what should be the next step? So I've repeated this like 3 times since the morning. So let me see. Whoever comes to the first answer. What's the next step?
Photoresist.
No, when I say next step, what is the next layer which is going to use? Like, is it going to be metallization or
SiO2.
SiO2? Okay. What else? What about others? So everyone says SiO2, SiO2, SiO2. Okay. And what about SiO2? Good. So what after SiO2? Where do you lay? Okay. Where do you do the SiO2? In which areas? What mask do you use to do SiO2? Do you use any mask or whole plane? Okay, whole plane. Good. And then after that? Rudra says metal, whole plane. And photoresist. Yeah, photoresist is assumed. I'm looking for what's the next sort of the layer which goes in, which will become your device, basically. I think everyone understands the photoresist part right now. Okay, metal. Everyone is saying metal, metal, metal. Okay. What about the source and drain? That's not formed yet, right? You remember the self-aligned? You you don't create the source and drain first. You create the metal, I mean thin oxide and gate first, and use the gate as a mask to do the source, self-aligned source and drain, right? Yeah, ion bombardment to do the source and drain diffusion. So you do your N plus and P plus implant. And what mask would you use for source and um, P plus and N plus implant? Which mask should I use? Should I use the, so by the way, this is called the diffusion mask. There's another mask which goes on top it called N implant, P implant, but just say, so this is called the diffusion mask. So diffusion is basically, in other words, people call it the active area, in the sense that's your source and drain. Okay. And this is your poly. Okay. So to do the P plus and the N plus implant, which mask should I use? Should I use, sorry, it's a mistake. 1 second, just let me correct this. They look so similar. This is your diffusion mask. So this is a N-type diffusion. This is a P-type diffusion. This is P-type. This is N-type. Okay. And this is obviously your N-well. And this is your P-well. So for the P plus implant and N plus implant, so there are three masks here. There is a P-well mask. There is a diffusion mask. There is a poly mask. Actually, there are 5 masks. The poly is the same between us. There's a N plus, P plus, diffusion, and then P well, N well mass. So let's start with N plus implant. So when I do the N plus, because N plus P plus is not done at the same time. First, one of them is done. Either you do N plus, then you do the P plus. Okay. So although in this figure I'm showing N plus P plus, but it is actually done one at a time. So let's do with N plus. So for N plus implant, with what's shown here, what mass should I use? No one? Okay, Ashwini says diffusion. Bhartirajan says diffusion. Anyone else? Prachita says diffusion. Yes, that's correct. So you want to use the diffusion mask because you want to implant yeah, you want to implant um, N plus and P plus only in this area. But since you have already done the gate, if you chose this whole mask, then it will do in this area and the gate will obstruct this and the gate itself will get diffused as well. And so that's the reason you want to do the diffusion on. Okay, implant on. And for P plus, you use the P diffusion. Okay, so looks like people are slowly getting it. And this is the salicide process which I was talking about. Oh, actually, Prajita, I think I was mistaken. Yeah, that's true. In a lot of process, so salicide actually, I said you use polymask. Actually, it is the diffusion mask because they want the source and drain to be pretty conductive as well. So they use that. But this is not for all processes. Like 130 nanometer plus, the saliciding is done for poly only. But looks like here they use this entire mask, this plus the poly, to do saliciding. So it makes the gate very conductive, as well as the source and drain also. I mean, the source and drain is already conductive, but the contact becomes a ohmic contact instead of a Schottky contact. So that's why they do it salicide. So this is when we do PN junction. Maybe I'll explain a little bit why you need ohmic contact. Okay, then you do the insulating material. By the way, that silicon dioxide you did, that was just purely to do masking. That is not to do this. So after that, you still do the insulating, where you actually isolate this from the next layer, because now you're going to start doing metallization. So you first bury all this in insulating material, which is in CMOS, this is SiO2, silicon dioxide, right? So you put silicon dioxide here, and then you can start putting metal layers in. After this, there are no devices, right? So it has to be only metal or capacitors. So metal to metal capacitors are also done on this top layer. Okay. And then obviously you need to make contacts to the top layer. So you do these holes, and typically this is tungsten. And the reason they use tungsten is, again, it's a processing thing. If you did aluminum or whatever it is, it's just that with holes, they'll not seep in. So you get very high resistive contacts. So tungsten works better. But now with higher end process, the metallization is copper, as well as the vias as well, which is much more conductive. It just process wise, for low cost processes, it's difficult to do with copper, because it oxidizes with silicon dioxide. So you do, so wherever you have the contacts, you take those masks. These are called the via mask. You take those masks and again follow the same process of photoresist and masking and all that, and create holes and fill them with tungsten. And those are what's called your vias, which are going to connect to your next level metal, right? And then after that, you do the deposition of metal. Again, take the metal masks. So these are your metal masks. So let's say this is M1, the first layer, metal 1, and you deposit metal 1, do photoresist, do all your patterning thing, and then you'll be left with metal just in the areas where you have drawn the layout. And now you start doing the connection. And then obviously you have more metal layers, like finer processes now have all the way up to 13, 14, I don't know, maybe 20 metal layers. The first monolithic process we started just had one metal layer. In fact, there are a lot of processes now we work with which just has 2 or 3 metal layers, because they're everything adds cost. Like I said, in IC design, everything is cost driven. Okay. Excuse me. Yeah, so then you go to the top level metal. So this is showing metal 2. Um, so this is your next level of metal layer, metal 2. So you again take the mask. So before you do that, obviously you do the same thing. You do the isolation from the next stage using silicon dioxide, and then do metal 2 here, and do the routing using the same patterning process and so on. And this is like I said, this is the STI process, where the isolation is done through this shallow trench isolation. And this is older process, which I think I showed you this slide before, which is called a local oxidation process called locus. Okay. Okay, another exercise for you guys. So you've already seen this. This is a locus process. And if I have to get this um, device fabricated, so I've shown, well, this is actually from the Western Estragian book, this is the West Estragian book. So if you look at the different layers, there are these layers. So silicon dioxide, N plus diffusion, P plus diffusion, polysilicon, and metal 1. This is P substrate. Basically, what I've said here is that these are the 5 steps you need to get there. What I want you to do now, will take a few minutes for you guys to work on this, is tell me the sequence. What is the sequence for you to get from a plain substrate, right, to this? So where would you, how would you arrange these 5 steps to get this? So you can just, you know, send it in the text. Um, this will be part of the assignment. You can upload it later as well. So I see 43125, 43215. Yeah, just everyone, you know, like as I said, these exercises are the ones where, you know, you'll kind of understand the material. Otherwise, you know, it'll be just a one-way kind of a lecture. Oh, sorry guys, I got muted by accident. Okay, let me repeat what I was saying. So I was just saying that a lot of you are still kind of imagining this process as like a PCB kind of process where you're taking few devices and connecting them by wires, but you have to realize this is a monolithic stack process, right? This is a stack, layer of stacks, and you go in the reverse direction, right? So you see the stack going from top to bottom, and when you're fabricating, obviously you go in the reverse direction. So I was saying that it's like that reverse poly calculators. If anyone has used it, it drives me nuts, but you put it in the stack whatever you want in order you want get calculated, right? It's like your C programming stack. So you have to kind of imagine as a stack. So for example, here you go NWell, and then you first do the poly because of the self-aligning, right? So that's the only difference why it's not following the stack. But other than that, everything else follows the stack. So after the poly comes the source drain diffusion, and then comes the salicide, which is not part of that layers, and then you have insulating layer, and then the contacts come first, right? Because that's the stack. You have the contact and then you have the metal, because by the time you reach metal, you can't do contacts anymore. So you have to first do the contacts before you go and do your metallization, right? Okay, so let's see. I think so what's 4 is NWell, so everyone got that right. And then 3 is N plus diffusion. Okay, some people changed it back. So after the N plus, what is it? It's in this step. There are obviously other steps, but I told you to just show me this 4 step. It is the polysilicon, right? So you do 4, 1. Then after that is your N plus P plus source and drain, right? So that will be 3. And then you do your contacts or your vias, right? That is 5. And then you do your metallization. So that's your sequence of steps. You just go kind of reverse in your stack. Okay, makes sense. Any questions? So I think finally Prachita got it right.
How come it's 5-2? It should be 2-5.
How come it's 5-2?
Yes, sir. Like the contacts will be at the last, no?
5-2, 5-2, 5-2. Makes sense?
Okay, sir.
Sumant, right? 5-2. Because if you do 5, you're done. You can't get to contact. I mean, if you're done to the metallization layer, you can't get to the contact because the contact is the next layer. You got it, right?
Yes, sir.
So 5 is the contact because those holes have to be made first before you do the metallization. Because you do the metallization, then how are you going to make those holes? Even if you have the mass, it cannot get penetrated through the metal, right? Because the metal overlaps. So let me take it back here. So the metal actually overlaps, right? So if I draw the 3D here, right? That's your 3D. So the metal is overlapping this contact area. So if you do the metal first and then try to do via, no amount of photoresist or anything will help you because you can't, I mean, even if you make a hole through this, then you have to do a tungsten all the way here. Then you will have all sorts of problems of alignment, right? I mean, it is physically possible. I'm not saying it's physically not possible, but you're just going to do a tungsten all throughout, and you're not going to get the alignment which you're going to get with this step, right? Steps 1 and 3, explain please. What is 1 and 3? Polysilicon and N plus diffusion. Okay, Ashwin, I think you have to, looks like you're stuck here. So you just have to take this offline, go through some of the material. You will understand. Anyone else wants the 1 and 3? I think I've gone through like what, 6 times right now from the morning. Anyone else wants? I mean, if a majority of people want it, I mean, we have time, we can cover it. But it's basically you cannot align if you did your diffusion first you cannot align the gate after that precisely. So what you do is you first do the gate and bombard the ions straight through the gate, and underneath the gate, automatically it will be stopped. So the only places which happens is the sides of the polysilicon, right? So basically you first, so this is the substrate, right? So you first do the thin oxide, right? And you do the polysilicon, right? So you do that. And then when you bombard the ions for diffusion, it will bombard everywhere else, including this area, but not underneath this area because the poly will block it. So you get automatically the source and drain aligned, which if you try to do it the other way around, where you first did the source and drain using the source and diffusion mask XORed with polysilicon, then you would get these two masks separately. If you did this and did the poly would be shifted this way or that way, and you'll basically get an open device. That's how they did it in older technology, but that was like, 10 micron devices. Now they are 2 nanometer devices. So you're talking about like 6 orders of magnitude. So it's so that's where the self-align helps you. So everyone is clear with this, right? Sir, SiO2 and metal layer under the soluble photo will be etched out. Which one? No, this is SiO2. So this, which one are you? Which SiO2 and metal layer are you talking about? The one shown in this figure? In the previous case. Oh, okay. And the assignment one, SiO2 metal layer under the soluble film. No. So you have to understand, right? So what I'm trying to do is wherever I did the layout, I want the metal and oxide to be there. Everywhere else, you want to dissolve it. So, but there are different combinations, right? You could get a combinations of where you are actually using um, photoresist to dissolve it or photoresist to block it, but whatever, you can choose whatever you want. That's not the point. I just wanted you to get a feel of like how you're going step by step, applying the mask and etching them out. So not sure if I still understand the question. Si2 metal layer under the soluble photoresist will be etched out. That's what you're trying to make, right? So that is what you decide. Wherever you want the metal layer to go, you want to make that photoresist soluble. The other places you don't want, right? So that's what you're trying to do. Like I said, you have the combinations of making the photoresist negative or positive, the mass positive or negative. So you can etch them in any fashion you want, but whatever you choose, you draw the layout accordingly. If you choose and say, I want to do positive mass, positive photoresist, and I want the metal and oxide to be there where the figures are drawn, then you choose the appropriate thing. But whatever you choose, you just stick to it, right? And then show the process. Okay, so I think everyone is clear so far. Okay, so I wanted to show just in a different way. I think the West book had this, so I thought this is a good way to show it, because people usually struggle in the beginning to understand the various steps. So if you, I've been saying you take layer by layer. Here in one shot, it shows you all the layers. So when you send an inverter layout, this is how an inverter layout looks like. And if you strip out all the layers out of it, this is how it will look like, right? And obviously, as I was explaining to Sumant earlier, if you have 1 million of these in your chip, you'll have the entire 1 million chips, 1 million devices, polysilicon in this mask, N-wells in this mask. So you only have same number of masks no matter how many devices, right? So the N-well for all the devices will be in the N-well mask, so that when they take the N-well mask, they'll just do the N-wells for all the devices at the time, and then they move to the next layer. Because this is a monolithic process, so you're going layer by layer. You're not going device by device. So that's why they can do it so fast, right? You have only 30 layers or 13 layers or 50 layers, but you have million devices. So you do all of the layers for every devices at the same time. So this is kind of a nice picture showing all the layers of different layers for the inverter. So you can see the NVL layer, the polysilicon, the diffusion, the P plus diffusion contacts, and metal one. And here also it shows a good step-by-step process for each of the masks. For example, you see for NVEL, you start with a P substrate, then you do the silicon dioxide, you do the photoresist, and then you etch up. So it's kind of a two-step masking. So you use the photoresist to create SiO2, which acts like the mask for diffusion, right? Because if you did diffusion with photoresist, it will just diffuse everywhere. So that's why you go through this process. So these are like 1, 2, 3, 4, 5, 6, 7, 8. So it's about 8 steps in this one mass. Once this is done, you have all your NVELs for whatever million, billion devices or one devices to be done. And then for the N plus diffusion and polysilicon, you can see it starts, obviously the NVEL is already done. So it does a thin oxide everywhere. It does a polysilicon everywhere. And then it takes the polysilicon mask and etches out everything else but wherever there needs to be gate, right? And then they do the mask opening for the diffusion ones after the poly is done. But they first do the N plus, right? So you can see it's only open for N plus. The P plus is still blocked by the photoresist. And then they do the N plus bombardment, and then they open up for the P plus. Oh, actually, I haven't shown the P plus one. So the next step is P plus one. So it's more than 8 steps, I guess. Okay, so P plus, actually, I do show it here. So P plus is done after that. And obviously, they'll block the rest of the devices when they're doing P plus. And then they do the metallization. The metallization kind of shown weird where it's shown that the metal actually goes into the vias. These are like the newer copper processes, but most processes you have to do tungsten vias and then do metallization after that. Yeah, hopefully, this is slowly getting clear. All right, so this is another exercise for you guys. This is also part of the assessment, which you should be up and live, hopefully tonight. And so basically what I've given you is I've given you 5 mask layers and I've drawn a layout. And what I want you to do is you just do the cross section. You don't have to draw step by step. You just, if you want to go step by step in your mind, it's fine, but just do the final cross section and then extract the IC device. Tell me this, what IC device do you get out of this? Okay, so you have 2 metal layers. If I do a Thevenin's or whatever S port parameter from these 2 port, what kind of device will it look like? Okay, so I'll give you some time, work on it. I won't say which device. It's part of the assignment, but I can if you draw the layers. Um, some of you may not get the device right away because you don't know about ohmic contacts, but you should. I think you should get an idea though. Anyone having problems with just doing the cross section, not able to understand what it is, or you can just come online and ask. But it's very critical to understand the underlying, and this is one of the complaints I get from the companies is that they are like we had a meeting with Intel recently, and they said, you know, the skill they're looking for is deeper understanding of both the device physics and process and software, actually writing codes. This is their PDK team, because they were saying, although, you know, they're writing design rule files and all that, a lot of the times they will come in and, you know, because they don't understand the underlying, you know, basic underlying processes, so they will not be able to figure out if something they're doing is wrong, or if they have to fix something, they have no clue. So these are the, you know, some of the things we are going through. Doesn't matter which branch of VLSI you go into, even if you go into design verification and you're writing, you know, Verilog code for the rest of your life, you still, it's a good idea to do it. Okay, so looks like, you know, a lot of people are getting it, so maybe I'll not even draw it. And so you guys just you know, upload it and do the assessment test, and maybe we can discuss it tomorrow or day after. Okay. All right, so I think that's all I had for today. So like I said, it'll be a shorter session. Any questions so far? Anything from morning class, or